Hello, Soham, can you hear me? Hi. Hi, this is Naresh. Yeah, I just logged in. So, I just had, it's nice the session you're doing. So, I just had a question for the guys who are attending. So, when do you expect the Fermi level to vary linearly with distance? No, not to you, Soham. I'm just asking the guys, if they have any input. Just any Lakshmi Kanta or Kushagra or somebody, Pranjal, you have any inputs? Or when do you think Fermi level can change linearly with distance? Guys, I think Soham was doing a nice job. So to make the maximum utilization, maybe if you can, any questions? Okay, if an electric field is applied, what happens when you apply an electric field? No, they messaged. I think Lakshmikant messaged.
So bands get bent.
Okay, bands get bent. And then in equilibrium, what should happen? Okay, Lakshmikant, another scenario, okay? Can you think of a scenario where the doping changes and the Fermi level changes linearly with distance? Non-uniform doping, did we talk about it in the course? Yes, okay. So that's one scenario, right? Because the Fermi level calculation, you have an ln, right? So if the doping density varies, let's say exponentially, then you will see a linear change in the Fermi level, isn't it? And that's why when when you have intrinsic carrier density, you have a Fermi level close to the mid gap. But then as you increase doping and you go to 10 power 17, 18, 19, it just goes to the edge of the conduction band, edge of the, close to the conduction band, let's say if you have electron doping, right? So even though you have 8, 9 orders of change in the carrier concentrations, you'll have only movement, gradual movement across the band gap, right? So that's one significant point that I wanted to you to note. Yeah. Any other, guys, just participate, because see, you can benefit more out of these sessions if you ask any question. No, no harm. Nobody's recording this also, I believe, right? Or are we? Oh, now we are recording. Okay, fine. Don't worry. Anyway, in any case, it's all right. See, one of the best ways to learn, guys, is to ask questions. When you ask questions, then a lot of your doubts will, you'll have a lot more doubts actually. If something will not make sense, then we can help you with that. I'm sorry. Yeah. Okay, anyway, Soham, continue, I think. Yeah. Soham, Soham. Yeah, I have a question here. So, what is the source of these electrons? Space charge that's coming out, right? But then, hello, can you hear me? Yeah, yeah. So if it's non-uniform doping, you'll have this space charge coming into picture. That is true. But another way of introducing excess charges could be you can shine a light, right? That's how. Yeah, you have electrons and holes created. Yeah, correct. Okay, nice. I just wanted to point out that. Yeah. Lakshmikant, you speak up, please. Can you speak up? Very nice. Yeah, good. Kushagra, thank you. Yeah, biasing. How will it help, Kushagra? You're injecting, is it? How will you create? But then you think about it, no? You have a piece of semiconductor. Let's say this is an N-type semiconductor or something. When you inject on one side, immediately the electrons on the other side have to go out, right? To complete the circuit. So how will you create excess electrons in one location?
Sir, doping, sir. Doping.
Doping. Doping is one way. Yeah. No, I'm just trying to interact and yeah. Doping is one way. Yeah, non-uniform doping you can get. But by biasing, can we get this non-uniform distribution of electrons?
No, sir. We need some external stimulus.
I mean, yeah. If you just take a simple N-type semiconductor, it won't. If you have a PN junction, of course, you can inject carriers into some regions and all that. Yeah. Right, Soham? No. The one of the answers was biasing. Kushagra said that. Okay, but biasing, I can inject excess electrons, right? If yeah, if you take a simple N-type semiconductor, then no, because the moment you inject on one side, it's like some resistivity, right? You can't have accumulation of charges anywhere. It has to flow out of the circuit. But if you have a PN junction, of course, you can have certain regions where you are injecting and so on. Yeah, that happens. Right. So this is okay. This is week 3. What have they figured? Week 3, right? Okay, then it's fine. Yeah. So these things are very useful in understanding PN junctions. Anyway, guys. Yeah. All right. Yeah. Go ahead.
It is not visible, sir.
Okay, sir. Now it's visible, sir.
Yes, sir. Yes, sir.
No, Kushagra. I think, sorry, not Kushagra. Soham. This is also similar question, right? Essentially. Similar question. Basically, you're given some concentration, you calculate the diffusion current and all that. Yeah. So no, but I just can you go back to the previous slide? Excuse me. Yeah. So this electric field, right? Just make note of this number. Okay. This is a typical number that you will see later on when you see PN junctions and so on. You will see that electric electric fields will be typically in the order of 10 power 4 volts per centimeter. Okay, you will calculate PN junction electric fields. It becomes very important later on. All right. One thing to note is when will you see electric field in a semiconductor? Okay. Kushagra, maybe we can just drop it anyways, 5 o'clock, right? And yeah, it's a similar question. I think the last question you can drop it, I think, isn't it? Or you have to do it. Yeah, close to 5, right? Yeah. So let's just try to emphasize this. When will you see an electric field in a semiconductor? Yeah. What is the condition for it? Gomati is from NPTEL office, is it? Or
No, sir.
no. Okay, fine. Yeah, I thought because we have an NPTEL office, somebody by name Gomati. We thought that you're from that. Okay. All right. So yeah, welcome Purvansh. You just joined at the end. So anybody, Gomati or Lakshmikant or Kushagra, any idea of when we will see electric field? What is the condition? If I take a simple piece of semiconductor, right, some doped semiconductor, will there be an electric field?
Yes, sir. There will be some electric field.
Where? If I apply a bias, of course, electric field is going to be there across the material, right? But if I don't apply any bias, will we see? No? Yeah, right. You don't see that, right? Suppose now, but then in this problem, I think Soham had taken a piece of semiconductor. Was it N-type semiconductor, Soham? I think it was N-type, yeah. He's seeing a electric field. Why do you think you see an electric field now?
It is due to the diffusion of
Diffusion? But diffusion, why does it create an electric field? See, I can take a case of, I think we have done non-equilibrium, right? Statistics. So if you just say simply pump electron hole pairs in a semiconductor, I just shine light on a semiconductor, okay? I can create lot of electron hole pairs and I will see diffusion of carriers. I will see in that. All right? In that case, will there be an electric field?
Yes, sir.
No. In that case, you will not. I mean, there will be diffusion and eventually just, it will basically, for electric field to be there, you need to have the background doping, okay? So basically the space charge has to be there. Only when you have space charge, because you will have an electric field. What is the fundamental, what is Gauss law? You remember what is Gauss law? In the differential form, it will be
in area.
Right? Flux in an area, right? E dot ds equal to q by epsilon naught. That is right. But we can also write it in the differential form. Okay? If you write it in differential form, what will it be, Soham? D by dx equal to? Gauss law. Basically, d by dx equal to the charge by epsilon naught, right? Yeah, please, because I'm not having the pen, right? So I just asked you to write the equation. You can see it in multiple ways, okay? If you can, this is an integral form of Gauss law, q by epsilon naught, that is what you're familiar with. But you can also write in the differential form, d by dx equal to, or I'll start with Laplace equation, Poisson equation, sorry. Laplacian square V equal to minus rho by epsilon naught, correct? Gradient of V is essentially electric field. So d by dx equal to q by epsilon naught, okay? The charge, it has to come from, it's not free charge. You have to remember that. It's the fixed charge, right? That will give you electric field, right? You see that? Yeah. So in this case also, in the diagram that he has shown, right? Just go back to the diagram. In the charges you showed, no? Wherein you put those charges and this one, yeah. So when these electrons move away, electrons are the free charges. They can go wherever they want, right? And because you have excess of electrons, they diffuse across the semiconductor. And what is left behind? The positive charge. That's the space charge we say, right? Because you are essentially introducing what type of dopants? It's an N-type semiconductor. What type of dopants? Can anybody say? Arsenic, boron, what sort of dopants you will have in this case? Phosphorus, right? N-type. So it has to be the fifth group. Let's say we put arsenic. Okay. When you put arsenic, N-type, right? Kumar, yeah. Thank you. So if you have an N-type semiconductor, you'll put an arsenic atom there. Arsenic has 5 atoms in the outermost shell. So the excess electron, right, which is not, in excess of 4, we have 5. So one of them will become completely free to move around. And then when it moves, the lattice site where the phosphorus atom was there acquires a positive charge, correct? Because we have taken, it was essentially neutral earlier, and then you have removed one electron, so you have a positive charge. That's why you get these positive charges, okay? And you will see later on that in a PN junction, you will have these space charge regions, and only there you will see electric field, okay? Right? Okay, then Soham, I have one question then. Let's consider, a piece of semiconductor, N-type semiconductor. We apply an electric field. Sorry, somebody was speaking. Lakshmikant, you had a question?
No, sir. What did you just said is a charge neutrality. We have to achieve charge neutrality.
Yes, charge neutrality has to be satisfied. That's why you have this space charge region that is created. Yes, you're right. No, I mean, I was trying to talk about a piece of semiconductor, let's say an N-type semiconductor, and we apply an electric field. We apply voltage to that. There will be an electric field, right? So now what will be the magnitude of that electric field compared to what you have shown? Let's say, take a 100 micron piece of semiconductor. What was the length of the semiconductor previously in the previous problem? 0.1 micrometer. Let's take 0.1 micrometer then, again, here also. Okay. And let's say how much voltage should you apply to get the same field that you got last time? Let's say 3000, right? Roughly 2500 volt per centimeter. How much should be the voltage that is applied? You take round of, divide by. Minus pi, right? Yeah. Volts, right? 100 megawatt volts. Okay. So it is a very, very large number that you have to apply. But then that is the thing, right? These electric fields that you are generating in the semiconductor are quite huge. If you have to do it by external application of voltage, it will take, you will not be able to realize that, right? That is the point I want you to appreciate. Okay. Later on in PN junctions, you will see, again, it will be a huge amount of electric field that's created. Okay. All right. Any other questions that you guys have? Gomati or Purvansh, you just joined newly.
Sir, actually, while solving the assignment for week 3, and there was one question, answer was not matching even after I checked multiple times, but answer was not matching. So,
you mailed in the group, discussion group?
No, sir, I didn't mail it. Shall I mail it?
Just message it. No, message it in the group. Anytime we will answer. Yeah, one of us will answer.
So we are there. So in which group?
The discussion forum for the I don't know. I mean, can you, Soham, you know the email address or something? I think they can post it, right? I'm not sure from your end how it looks.
Yeah, yeah. Oh, okay, okay. Okay, sure. I will upload it there only.
Yeah, please mention it. Anytime you see any issue, right? Please mention
Yes,
it. And I mean, see, we'll try to answer it over the chat. If you prefer a one-to-one conversation, we can even do that. You know, I just have this question. Can I discuss with you for 5 minutes or something? You say, we will arrange an online call and we'll answer your questions. We are there to help you. Okay. But then you guys have to come forward and then interact with us. We're not going to eat you if you speak. Okay.
Yes, sir. Sir, actually, the question was basically based on direction-based question. So, actually, first question it was easily answered, but next question was also very easy, but answer was not even matching with any of the options. So, I thought.
Yeah. So what? Yeah, we can do that. We'll answer it directly if it's possible. If you still don't understand, we are always, we can schedule a one-to-one phone call or whatever. No, not phone call, but yeah, a Google Meet. Okay.
Okay, sir. Okay, sir.
Please feel free to ask any questions that you have. Okay. It's very, very important. From our side, at least, I like to talk with you guys because I can understand, where are the gaps in understanding and I can try to help you.
Yes, sir, sure.
And I think we are due for a, interactive session, right? Live interactive session with me. I think it's close to 1 month now or 3 weeks. So would you guys want that? You have any doubts that, what is it? What is the feedback?
Okay, sir. No doubts.
No doubts. Okay. No, I'll be available maybe in maybe in the last week of August or something. We'll try to schedule one. Please, but that will not, I will not solve problems or anything. I'll just try to clear conceptual issues if you have anything. Okay. I think I'll let you finish the PN junctions. Then I think I'll do that. Kushagra. Gomati, you wanted to speak something?
No, sir. I said, okay, sir. We'll follow it up. I said.
Yeah. How are you finding the course?
Actually, it is good, sir.
Is it a little bit heavy?
Yes. Sir, it's not little bit heavy.
It's very heavy, yeah?
Yes, sir. Yes, sir.
I see. See, the reason is, semiconductors are one of the most core areas, right, in today's technology.
Okay, sir. Okay, sir.
And we can do it lightly also. The issue is, there is so much more. Generally, what happens is in the first course, we do very little. Then later on, it becomes much more. There's a lot more to study actually. That's why. And also we have all this, India Semiconductor and all that.
Sir, actually.
Sorry, yeah, tell me. Gomati, please go ahead. Gomati, you're saying something. I'm sorry, I missed it.
Yeah.
Okay.
So directly we'll move on to the devices. So directly we'll be moving on to the devices, and it's not like this. So directly we'll move on the devices, equations, everything, sir. So thank you so much. Now I have learned.
I see. No, you'll have devices now, and also later on we'll talk about MOS capacitors, MOSFETs. I think, yeah.
Okay, sir.
I want you to go beyond the equations. The equations are okay. Yes. We have to develop an intuition because the latest things are all much more, it's all interlinked. That's why. Yeah.
Okay, sir. Thank you, sir.
No, yeah, it's okay. Sure. All right. Please, email, message. Yeah, message on the group. Sorry? Lakshmikant?
It's much requiring semiconductor modeling, like MOSFET modeling, FinFET modeling, simulation.
Of course. If you want to work on the latest generation devices, you have to know all these things very nicely. And yeah, sure. Kushagra, you had something? Kushagra, can you speak?
Yes, sir.
How are you finding the course?
The course is very good.
Do you have any questions? You asked me a couple of questions online. I saw that. But
yes, sir. I am taking your another course also, quantum photonics.
Yes. We are going along in that. Yes. Where are you from?
Sir, I am from Indore.
Indore. Not that. Which college?
SGS ITS.
I see. Okay. Yeah. Just keep asking questions. We'll be happy to answer. Yeah.
Yes.
Anything that you find, is tough and not able to understand?
It's okay.
Yeah.
Sir, my opinion is that Friday evening I attended the classes, sir, 6 to 7. I feel that is better, little bit slower. But today it went on with much more speed. I'm trying to recognize the formula myself, but further it will be moving on to next few more steps. So what I feel is that the Friday's class was little bit slower, though they convert
Okay,
or
sir.
solve
It was
all
a
the
little bit
problems.
fast, but it was okay, sir. No worries, sir.
Yes, sir.
No. So I think what happens is,
According to my opinion.
no, that's absolutely right, Gomati. And yeah. So
Okay, yes.
what's happening is somebody is more familiar with the formula. Then if you go slow, they will say that you're going too slow. Somebody may not
Yes,
be
sir,
familiar
yes.
with the concept. Then we have to
Yeah.
go very, very slowly. So it's very
I
difficult from an instructor. I mean, and Soham also is actually a student still. So he's also learning. So the best way, I think, anytime you feel that something is not very clear, no, stop him. Stop him. No
yes, sir.
compromise. There is
Yes, sir.
there is no restriction or there is no mandate for Soham to cover something. Unless we are able to help you, the whole session is pointless. So anytime
Thank
you're
you.
going slow, you're going too fast. Can you please explain
Yes.
this one more time? Welcome. We'll be happy to do that. Okay.
Yes, sir. Thank you, sir.
Yeah. Anytime. I mean, if you feel that okay, it's going too slow, yeah, whatever. Anything you should ask. Otherwise, Soham won't know what to do. Actually, I mean, he's confused. Right? Yeah. Yes. Yes. Yeah. All right. If there are no other questions, we can sign out and yeah. Lakshmikant, yeah, please go ahead.
Thank you, sir.
No, sir, it is understandable. Okay. Thank you. Thank you so much, sir.
Yes, sir. Yes, sir.
Thank you, sir.